Okay, so let's okay, try to finish this class. Okay, last hour. Okay, so suppose you are studying the number of active users per hour on your website or daily temperature in your city. Okay, these two problems. Okay, active users per hour or daily temperature in your city. These two, you have only you pretty much have only one number per time step, right? Okay, I mean at each step you have a particular number of active users, or at each day, okay, you have a temperature in your city. Okay, so those two things are just you're trying to get a single number, okay? Or your company's financial health measured quarterly using multiple metrics. So this is a little bit more complicated, okay? Because you are measuring your company financial health, okay? And there are multiple metrics. So this means at each quarter you need to estimate like a set of numbers. Okay, so no matter in all these cases, the data will be a sequence of one or more values per time step. Okay, for the first two, each time step you have one value. For the last one, okay, each time step you have multiple values. Okay, so this is called a time series. Okay, so in the first two examples, there is a single value per time step. So these are called univariate time series. Okay, so this is what we call univariate time series. Okay, the last one, okay, the financial example, there are multiple values per time step. Okay, for example, the company revenue, debt, and other stuff. Okay, so it is a multivariate time series. Okay, so typical task is to predict future values. Okay, either the future active number of active users or future temperature, like the temperature for tomorrow maybe. Okay, or like the company financial health for the next quarter. Okay, so you are predicting this. Okay, this type of approach is called forecasting. Okay, another common task is to fill in the blanks. Okay, sometimes the data set has some empty, some missing values. Okay, those are blanks. Okay, to predict or post-dict the missing values from the past. Okay, so this is called imputation. Okay, imputation is to fill in the missing value, pretty much. Okay, so for example, the figure in next slide shows 3 univariate time series, each of them 50 time steps long. And the goal here is to forecast the value at the next time step, okay, which is represented by the x for each of them. So this, you can see, this is time series, and you have first 50 steps, and the last one, the one you want to predict is here. And this one, okay, you have first 50 values for the first 50 time steps, and last value you want to predict is here. The next value you want to predict, and this one is something like this. Next value you want to predict here. Okay. So this is the thing that we want to deal with. Time series forecasting. Okay. So, okay, for simplicity, we can use a time series generated by the generate time series function. Okay, so we create a generate time series function. So it is like this. This is a very simple function. Okay, so generate time series. We the batch size and the number of steps are the arguments to pass to this function. Okay, so we have frequency 1, frequency 2, offsets 1, offsets 2. Okay, we randomly generate these 4 numbers. Okay, and time equal to this linear space. Okay, you know, we prepare this. I mean, for each batch, for each batch, we have a number of steps. Get them ready, and then okay, you can see series equal to 0.5 times. This is sine, right? I mean, you guys should be familiar with that triangle. You know, like those sine, cosine, those stuff. Okay, so this is non-pi sine. Okay, time minus offset 1 times the frequency times 10 plus 10. Okay, this is wave. This represents wave 1. Okay, so we first add this to the series, and then we add another wave. Okay, which is defined by this one, 0.2 times sine of this thing. Okay, so this is a sum of 2 waves, and then we also, you know, add a noise here. We add another noise. Okay, and then we return this series. Okay, so this is like well, the microphone is dead. Okay, anyway, so we are going to, you know, we basically here we use these 2 waves. We add up these 2 waves and add some noise. Okay, and use this as our time series. Okay, so this function creates as many time series as requested. Okay, so how many time series? Okay, defined by the batch size argument. Okay, so each of length n steps. Again, this n step is defined by the argument. Okay, and there is just 1 value per time step in each series. Basically, it's like you know, controlled by this. Okay, so all series are univariate. Okay, the function returns a non-pi array of shape, batch size, time steps 1. Okay, the reason this is 1 is because it's univariate. Okay, so where each series is the sum of 2 sine waves of fixed amplitude and but random frequencies and phases. Okay, plus a bit of noise. Okay, so something like this. Very simple. This is very simple data that we create. Okay, we want to, you know, use it. I mean, as an example to showcase how we can predict, like this. We can deal with this, you know, prediction. Okay, because if you want to do the prediction, you need to know the ground truth, right? So here, okay, see the n step is 50. Okay, the series is like a generate equal to generate time series. Okay, like 10,000 n steps plus 1. Okay, this is like, so we have 10,000 series. Okay, because we have each batch has 10,000 series. Okay, well, we have only this batch. Okay, 10,000, and each series is like a 50 plus 1. Why is it plus 1? Because we want to predict the next one. Okay, so actually each series will have to generate 51 value. Okay, and then okay, we will break this series into training set, validation set, and test set. Okay, so I think this is very easy to explain. You know, so I will not go into a detail here. Okay, so we have training set, validation set, and test set ready. Okay, the first 7,000 series are used for the training set. The 7,000 to 9,000, these 2,000 series are used as a validation set, and the last 1,000 is used for the test set. Okay, and then okay, so before we you know, design our RNN model, okay, we want to you know, have some baseline model to compare with. Otherwise, you don't know how good or how bad your RNN model performs, right? So, yeah. So there's like a simplest approach to predict the last value in each series, okay? This is called naive forecasting, okay? This is provided actually by Python. Okay, Python actually has like a default naive forecasting function that you could sort of use. Okay, so it's sometimes surprisingly difficult to outperform. Okay, in this case, okay, you try to use, okay, I mean, y predict equal to this x valid, okay, -1. Okay, I mean, it will automatically fill the last value for you, and then you try to compare this prediction with the real with the generated value, okay, that we know. The ground truth that we know. So you calculate the mean square error, and the mean square error is 0.020, 211, blah blah blah. Okay, you get the idea. So this is actually pretty good, right? Pretty good. Okay, 0.02. I mean, quite low, right? And then, okay, another easy approach that we can use for we can use as a comparison is like we can use a fully connected network. Okay, a very simple fully connected network like this. Keras models sequential. Okay, in this model, we first have a flattened layer of shape 50. Okay, 1. And then, okay, because we want to output the prediction, right? So we just output a dense, the output layer is only 1 neuron. Okay, so be very careful here, okay? In this, we could say this is a multi-layer perceptron, but really, it does not have any hidden layer, right? This is input layer, this is output layer, and we don't have any hidden layer in between, right? So to be honest, this is more like a perceptron. Okay, this is more like a perceptron. Okay, so we can refer this one. Okay, you know perceptron. I mean, we talk about perceptron like at the beginning of this semester, right? I told you guys perceptron is a linear model, right? Okay, yeah, I mean, we have 50 neurons. And this 50 neuron will connect to this dense layer, with 50 connections. So each connection has a weight, okay? And we also have bias. So yeah, you can use the MSE loss as a default, and then you train this for 20 epochs, and using Adam, using Adam optimizer, and the MSE, okay, if you use the validation set, MSE is like 0.004. It's pretty good, right? Pretty good. It's better than the naive forecast. Okay, naive forecast. Naive forecast is 0.02. This one is 0.004, which is 5 times better than the naive forecasting, right? Okay, so we want to see if we are able to, if we use RNN, can we outperform this, these two baseline? Okay, so the first one is a very simple. Okay, so we just create a simple RNN with 1 neuron. Okay, so input shape is none, 1. None means it accepts any size of the input. Okay, and each input size is 1. Okay, because it's univariate. Okay, and then if you do not set the we do not need to specify the length of the input sequence. Okay, since a recurrent neural network can process any number of time steps. Okay, so we can train this model. Okay. Oh, by the way, by default, Okay, you don't see like a activation function here, but the simple RNN layer by default use hypertangent. Okay, by default use hypertangent. Okay, so yeah, it's just like the easiest like a simple RNN that which the h is equal to y, by the way. Okay, and the first and initially like the previous feedback is 0. Okay, just like what we described earlier. Okay, so it's going to take the x0, x1, x2 up to x49, and it is not going. All the output will be ignored until the last one, y49. It's going to be used for to compare with like the ground truth. So so you can imagine. Okay, so in this model, actually we have to expand this to 50 time steps, and the last one will be used to compare with the ground truth, right? Which will flow back. Okay, the arrow will become flat gradient to flow back to do the certain modification to the weights. Okay, and during the training. Okay, so yeah, and also okay. The recurrent layer in Keras only return the final output, okay, by default. So to make them return one input per time step, okay, in other words, like to output sequence, okay, if you get a sequence, you want it to output sequence, then you have to set return sequence equal to true. Okay, I mean, you will see this later on, okay. So if you compile, fit, evaluate this model, okay, train for like 20 epoch using Atom, and the MSE will reach 0.014. So, well, it's better than the naive approach, right? But it's not as good as the simple linear model. This simple linear model is referring to that fully connected well, you can say it's MLP, well, but actually it is pretty much just a perceptron model, okay? So why is that? Because that perceptron model, okay, as I said, okay, we have 50 connections, including one bias. Totally, we have 51. We have 51 weights, right? 51 parameters. But for this simple RNN, we have only one neuron, right? For that one neuron, how many parameters do we have? We have one weight because it's a univariate, right? We have one weight for this input. We have one weight for this one, and one additional weight for the bias. So totally, for that simple RNN, we only have 3 parameters. Okay, to train. Okay, to tune, basically. So yeah, from the information theory point of view, this is really this model is really too simple. Okay, too simple to get a good result. Okay, I mean, think about this. Okay, with just 3 parameters. Okay, it already reached like 0.014. It's not too bad actually. It's not really that bad. Okay. Compared, I mean, with like the linear model which has 51 parameter, and yeah, I mean that one outperformed this, but really like in terms of if you compare the number of parameters, I mean, really like that's understandable. Okay, so our simple RNN was too simple to get good performance. So let's try to add more recurrent layers. Okay, so the first thing, okay, we could add is that we can add more layers. Okay, I mean, if you want, we can add more neurons per layer as well. Okay, but if you remember, like just like any other neural networks, okay, adding for the same number of parameters, a network with more layer is more powerful than a network with more neuron per layer. Okay, so yeah, I mean, even though we can add more neurons per layer in this case, I mean, it's probably a better idea to just add more layer. Okay, so there are many other models to forecast time series, such as weighted moving average model or autoregressive integrated moving average. This is abbreviated as ARIMA. I'm not sure if your background is from mathematics or statistics. I mean, this word ARIMA should ring a bell to you. Okay, this is like one famous model that is used to predict the time series data. Okay, but I mean, some of them require you to first remove the trend and the seasonality. What is trend and seasonality? Okay, for example, if you're studying a number of active users on your website, and we know from a prior knowledge that this number of active user actually growing by 10% every month. So you could, what you can do is that you can remove this trend from the time series. Okay, you can, for the training data, because it must be, from many previous months, right? So you can remove like that 10% extra active users from all the data training data set, and then use that to do the training. Okay, and then after you get the prediction, you can add that the trend back to get the final prediction. Okay, this will usually make the prediction better. Okay, this usually will make prediction better. So this is for the trend, right? Another one is seasonality. What is seasonality? For example, if you want to predict, trying to predict the amount of sunscreen lotion sold every month. Okay, well, we know sunscreen lotion is probably used for people who go swimming, right? Okay, if you go to beach, then to avoid sunburn, you use sunscreen, right? So obviously, I mean, this type of goods sell better in the summertime, right? Okay, and it doesn't sell that well in the winter time, right? We know that, right? We know that. So if you try to see it's the amount of sunscreen lotion sold every month, then you will see sort of like a peak during the summer, and for the other season, especially winter season, you will see pretty much not too many people buy sunscreen. Well, for some people, in US, there are some female who likes to get certain sunburn. Okay, there's sunburn machine. You can lie down in that machine to get a tan. Okay, I mean, to make your skin look dark. But of course, when you go into that machine, you should also apply sun lotion to avoid damaging your skin. Okay, yeah, I mean, so I'm not saying in the winter time nobody will buy sunscreen lotion. It's just like a number of people who buy the sunscreen lotion. Obviously, is much smaller, right? This is understandable. Okay, so this type of goods has seasonality. This is what the seasonality means. Okay, so how do we avoid, remove this seasonality? Okay, we can use the technique called the differencing. Okay, we basically just obtain the difference between the value at each time step and the value 1 year earlier. Okay, we use that different value as our data set. Okay, I mean, yeah, summertime is sales better, but last year also summer sales better, right? So the large number minus large number, the difference will still be reasonably small, right? So if you do this differencing, use this differencing technique, then you are able to remove that seasonality, and then you do a prediction, okay, by using your model. And once you finish the prediction, you can add the seasonality back. You can add the seasonal pattern back to get the final predictions. Okay, so get rid of the trend or seasonality, okay, and do a prediction, and then add the trend and seasonality back. Okay, this type of thing, okay, is very important for like weighted moving average model or like ARIMA. Okay, this type of statistical approach. It is actually also, I mean, if you use RNN, it's not that necessary to use this, but it may also improve performance in some cases, because the model will not have to learn the trend or the seasonality. So the model learns, what should I say? Like it learns like you only need to learn smaller amount of information, right? So sometimes it can help your the prediction to be better, okay, to perform better. So this is like one thing you can consider. But I'm not saying like we are going to do that here, because, well, for the data we just generated, I mean it's just a very simple 2 sine wave plus some random number. So really like it's difficult to say there are certain seasonality or trends. I mean, but you get an idea. Okay, if your application has trend or seasonality, I mean, it is a good idea to get rid of them. Then do the prediction, okay, and then add them back, add the trend or seasonality back. Okay. So so now it comes to the multi-layer. Okay, so it's quite common to stack multiple layers of cells. Okay, so as shown in the next figure, we call this a deep RNN. This one. Okay, so I mean in Keras, okay, in TF.Keras, okay, it's very simple. Just stack recurrent layers, just like this. Okay, we still use sequential API, and Keras layers, simple RNN, and you can see that we also increase the number of neurons. The first layer we have 20 RNN neurons, and we set return sequence to be true because we want to output sequence, because the next layer is also RNN. So the RNN layer will expect the sequence. Okay, the RNN layer expects sequence. So we have to set return sequence to be true. Okay, and then the next layer is also 20 neuron return sequence to be true. Okay, and then the last one, okay, it's a simple RNN with 1 neuron. Okay, it also expects the time series data, but because we didn't set return sequence to be true, so you only output the last number. You only output the last number. So, by the way, how many parameters are we talking about here? each of these has two weights, right? The weight for the what should I say, like the input, and the weight for the feedback, right? So we have 40, around 40, okay, another 40, and well, we probably need to add some like bias, okay, and we have 3, so totally about like about 50, 60, something like that. So the reason to make it like this is just to make sure the number of parameters is roughly the same as the number of parameters in that linear model. Okay, the linear model is 51 parameter, right? This one, for this one, the number of parameters is roughly the same. Okay, it's well, I should say slightly more, but not by much. Not by much. Okay, so you can train the. So yeah, I mean I already explained that. So if you compile, fit, and evaluate this model, you'll find that it reaches an MSE of 0.003. So we managed to beat the linear model. Okay, so you say, oh, it's just better by 0.001. Okay, because the linear model is MSE is 0.004, right? So it's only good for like a 0.001. But in terms of percentage, it's significant because it's 25% better, right? It's 25% better. So it is considered, I mean, a much improved performance. Okay? But there are some stuff that we can improve on this model. Okay? Because the last layer, okay, we use a single unit because we want to forecast a univariate time series. And this means we must have a single output value per time step. Okay, so having a single unit means that the hidden state is just a single number. It means like the single, if you really consider, remember like the example I show you, I told you, okay, you are going to, the last layer, okay, you are going to expand 50 time step, and only the last one will be, the output of the last one will be used to compare with the ground truth, right? So we will have like a gradient flow back and to do all this. But you know, if you don't have like the gradient to come back from here, I mean, and having the gradient to flow back all the way 50 steps, I mean, it doesn't make much sense. I mean, those like, you know, you really don't need to have use the time. You really don't need to use the simple RNN for the last layer. For the last layer. So what you can do is actually you can replace. You can replace where is it? Sorry, go too far. Yeah, you can replace the last layer by a dense layer. Just use like one, you know, one neuron there, okay, and it has almost the same effect anyway, okay. But if this one is a dense layer, then okay, you don't have to, because this one doesn't expect the sequence input. So this one on the previous layer doesn't need to set the return sequence to be true anymore. Okay, so you have this. You just change to the dense layer, and there's another benefit of this. Okay, because like in the previous model, because the last layer we are using hypertension by default, right? But if you want to use a different activation function, then it is perhaps better to use dense layer, because in the dense layer it is more easily to incorporate different activation function. This is especially the case if your predicted value is, for example, within certain range. Okay, for example, I mean, if it's positive, remember, if it's positive, we prefer to use, for example, ReRU, right? Okay, but I mean, in a previous example, I mean, in the previous model, okay, because the simple RN use hypertangent by default, so you know, it's difficult. I mean, we have to change that activation function. So you know, if you use dense layer with one neuron, then it's easier for us to control that. Okay, so this is one additional benefit, and then you will find that this model, if you train it and they compile it, okay, first it converges faster, okay, because well, there are several reasons for that. First, the last layer doesn't need to go through the back propagation through time, right? The back propagation through time, you know, is require more resource to train than the dense layer, okay? And the second, because dense layer, I mean, as I said, like by default, dense layer activation function is ReRU. ReRU activation function is easier to converge than hypertangent. So, I mean, because of these considerations, so you will find that this model converges faster and it performs just as well. Okay, it performs just as well. I mean, I think like performance is still like 0.003, something like that. So plus you could change the output activation function if you want. Okay. So far we only predict one. I mean, from the past 50 time step, we only predict one number, right? We predict next value, right? But what if you want to predict like several time steps ahead? This is kind of like you know, the project number 3. Okay, you want to predict like PM 2.5, not just 1 hour, but like 6 hours in in advance, right? So what do we do? Okay, you could, okay, remember, because we have like our model, the model that we just trained is able to predict 1 hour, right? So you can do something like that. We predict 1 hour and then move the input from the past 50 to past 49 plus the newly predicted one. And then we'll predict the next hour. Okay, we keep shifting and then predict the next hour and so on. Okay, so this is doable. This is doable. Okay, of course, I mean, if you want to do that, I mean, you have to change like the data set. I mean, in order for you to do that. But yeah, this is doable. Okay, you just like apply this model multiple times to get like several time steps ahead. Actually, I mean, here we want to predict like this time step 10 steps ahead. Okay, this is quite more difficult than the previous problem, because previous problem only require you to predict one time step ahead. Now we need to predict 10 time steps ahead with the same amount of information. Okay, so what happens is that, as you might expect it, the prediction for the next step will usually be more accurate than the predictions for later time steps. Why? Because the prediction, the first time step prediction, okay, you have a smaller error, right? You have smaller error, but that small error, because you use it as like as input for the next time step, right? To predict the next time step. So the error actually add up. The error actually add up. So it's going to be something like this. The blue cross represent the real value, okay, for the next time step. But the red point represent the predicted value, okay, when you apply this model 10 times. And you can see that the error, accumulated. It becomes bigger and bigger for the, for the following time steps. So this is perhaps not necessarily a good approach. Not necessarily a good approach. Okay, so what do we do? Okay, I mean, if you wonder what this piece of code is, this piece of code is just we also need to generate because we want to predict from the past 50 time step, we want to predict the next 10 time steps. So we have to generate 60. So this is we do the plus 10, not plus 1. The other part is pretty much the same. Okay, and also, okay, what is the performance? Okay, so the naive approach, okay, this is terrible. Okay, it gives a MSE of about 0.223. This MSE is calculated by the prediction you have for the next 10 time steps. So 0.223. But the linear model gives an MSE about 0.01188. So linear model is actually better, okay, much better than using the RNN to forecast one step at a time, okay, to do this 10 times, okay, and also much faster to train and run, okay. So so what do we do? Okay, so here, okay, well, what you can do is that you can train and run your RNN to predict actually 10 time step. Okay, so here you can see, okay, before doing that, of course, you have to prepare your training set so that the ground truth is not just one number but 10 numbers. Okay, so here in the model you can see here, okay, 20, and dense layer you output 10 numbers. Okay, so instead of just outputting one number, you output 10 numbers directly. This 10 number you try to fit the next 10 numbers, okay, from this time series. And if you do that, okay, after training this model, you can predict next 10 value at once, okay, and the result, okay, it works nicely. Okay, the MSE for next 10 time step is about 0.008. So this is pretty good, right? It obviously outperforms the linear model by a lot. Okay, that's much better than the linear model. But we can still do better. Okay, indeed, instead of training the model to forecast next 10 values only at the very last time step, we can train it to forecast next 10 values at each and every time step. Okay, so we can convert now. What we are doing here, okay, up to now, we are doing sequence to vector. Sequence to vector. But now, okay, the next one, what we can do is we can actually convert this model into sequence to sequence. In other words, originally, the model we were using is this one. But now we can convert it to like this. Okay, but well, I think I'm out of time. Okay, we will talk about this next week. Okay, we'll talk about this out next week. I think we will finish this chapter next week, and then be able to advance. Not sure if we can advance to the next chapter, but at least before the end of this semester, I expect we finish the autoencoder part, okay, of the next set of slides. Okay, so any question? If no question.